today we're going to talk about an electrolytic cell and draw a diagram of an electrolytic cell. Before we draw the diagram, I think it's a good idea to compare to the type of cell we already know, which is a voltaic cell or a galvanic cell. And so when we talk about a voltaic cell, we know that it is spontaneous. Which means that the electrons want to flow from the anode to the cathode. In an electrolytic cell, the new cell we're looking at, it's non-spontaneous. The electrons do not want to flow from the anode to the cathode. And so how do we get a non-spontaneous reaction to take place? We have to put in energy. So an electrolytic cell is endothermic. While a galvanic cell is exothermic. Energy is given off. And so galvanic cells, a chemical change creates electrical energy. But in an electrolytic cell, the electrical energy produces a chemical change. So an example of this from first year chem was in the types of chemical reactions chapter when we did the demo with the decomposition of water. It required a battery, and we're going to look at today the electrolysis of water and how that's set up. In terms of cell potential, we know that a galvanic cell has a positive cell potential, while an electrolytic cell has a negative cell potential. So the uses of a galvanic cell are batteries and fuel cells, which you're reading about later this week. Uses of an electrolytic cell are charging a battery, producing aluminum metal, and chrome plating an object, which you're going to read about, and we're also going to talk about in today's lesson. So let's look at a diagram of a voltaic cell. So on the left-hand side, and this is from your book, page 729. On the left-hand side is a galvanic cell. On the right-hand side is the new cell we're looking at, an electrolytic cell. So I would recommend pausing the video and sketching the electrolytic cell. And so we know at the anode we have oxidation. And the cathode we have reduction. So if we look at our two cells, the one on the left we've drawn before, the one on the right is new, but both have an anode and a cathode. Both contain ions in solution. These are both zinc sulfate and copper 2 sulfate solutions. They both contain metal electrodes. The electron flow in both is anode to cathode. There is a salt bridge present, or a semi-permeable membrane present. And we can see that the anions flow to the anode and the cations flow to the cathode in both cells. What is different is that in the galvanic cell, at the cathode, we put the solution with the ions with a higher reduction potential. But in an electrolytic cell, the anode contains the ions with the higher reduction potential. And this is what gives us our negative cell potential. So let's look at the electrolysis of water. Let me just move this over a little bit, this picture, so we can talk about it. So what we have on the left-hand side is our anode. This is the anode, and it produces oxygen. So at the top here, this is the oxygen gas being produced. On the right-hand side is the cathode, and that produces hydrogen gas. And you can see there's twice as much hydrogen produced than oxygen, and that will be seen in the net reaction. Now, pure water contains few ions, so a negligible current will flow. You put the platinum electrode in, and you wouldn't really see the oxygen and hydrogen gas forming. But just a small amount of a soluble salt causes this formation of hydrogen and oxygen gas. And in first year chem, we did this with a pencil. We used graphite as our electrode and a 9-volt battery and a petri dish, and you could see the bubbles forming at the end of the graphite. So the reaction on the anode side, water is forming oxygen gas, hydrogen ions, and electrons. On the cathode side, water plus electrons forms hydrogen gas plus hydroxide ions. And so when you combine these reactions together, these half reactions together, you will get 2 water molecules forming hydrogen gas plus oxygen gas. And you can see that for every 1 mole of oxygen gas, there's 2 moles of hydrogen gas formed. And this is obvious in the picture, the diagram here. You have twice as much hydrogen gas in the tube. The last thing we need to talk about in terms of electrolysis is plating out. So let's say I have a mixture in an electrolytic cell. It has copper, silver, and zinc. If initially the voltage is really low and gradually turned up, in what order will those metals, the copper, silver, and zinc, be plated out onto the cathode? So the first thing we need to know is that plating out refers to reduction. And so we need to look at the standard reduction potential table, potentials in your book on page 709. And so for copper, it has a cell potential equal to 0.34 volts. For silver, it has a cell potential of 0.80 volts. And for zinc, it has a cell potential of negative 0.76 volts. So in terms of plating out, since this is a standard reduction potentials, the highest in the table will plate out first. So silver has the highest. So this would plate out first. And then we would have copper second, because that's the next one. And then zinc has the lowest cell potential, so it would be the third one. So it would go silver, copper, and zinc. And so that's how you determine what ions, if you have a mixture, will plate out first onto the cathode.